Hey everyone, this is Dr. Walker. In this video, I'd like to go over the second example of v582 on magnetic flux. In this example, we have a straight current-carrying wire with the current going up, and we have a loop to the right of it, a rectangular loop. We want to find a flux through this loop due to this wire. So we know that to have magnetic flux through a loop, you must have a field going through that loop. And there must be a component of that field that is perpendicular to the plane of the loop. In this case, the field is produced by the wire. At the location of the loop, the field goes into the page. That's the X's that have been drawn as the magnetic field due to the wire. We know that it goes into the page to the right of the wire using right-hand rule number 2 with the thumb pointing in the direction of the current and the fingers curling in the direction of the magnetic field. We also know the magnitude of this field is mu naught I over 2 pi r. This is the field due to a straight wire. So this loop, different parts of it are at different distances from the wire. So the field is not constant through the loop. When you're closer to the wire, you have a stronger field. When you're further from the wire, like over here on the right-hand side, you have a weaker field. When you have a changing field, or not a changing field, but a field that is not constant, then we cannot use our simple definition of magnetic flux, which was BA cosine theta, where cosine theta made sure that we had a perpendicular component of the magnetic field going through that loop. So in this case, we need to use the general equation for magnetic flux, which was provided in the lecture notes, and it's the integral of B dot dA. This is very similar to when we did electric flux. If we didn't have a constant electric field, or if we didn't have a flat surface, we had to use the integral form to find electric flux. We had to do E dot dA. We couldn't just do EA cosine theta. Same thing for magnetic flux. In this case, we do have a flat surface, but we have a field that is not constant. So that's why we have to use this form of the equation to find the flux. Now, for the dot product, we know that if the field is perpendicular to the plane of that surface, then we know that the dot product vanishes because remember the area vector points in a direction perpendicular to the surface. So we can assign a direction for dA, which is perpendicular to this surface here and goes into the page just like the magnetic field. So the dot product vanishes and it's just going to be BdA. So now we can go ahead and plug in what we know. The magnetic field, its magnitude is mu naught I over 2 pi r. And then we need an expression for dA. We did a very similar example with electric flux through a rectangular surface. It was in video 514. I encourage you to look at it. But what we did to get dA here is we looked at a strip of our rectangular surface here. Because we know that the length b is going to be constant for the whole loop, but we're going to integrate along the horizontal direction here. If we have a strip that has a width dr, since we know that the field varies with r, we're going to integrate along this horizontal direction, which we can call r in this case. So the dA is going to be b dr, right? The length times the width, and we're going to integrate over that width from a distance c all the way to the second distance right here, which is c plus a. And now we can go ahead and do this integral to get the magnetic flux. We're going to take out the constants, mu naught I b over 2 pi. we're going to be left with an integral of 1 over r dr from c to c plus a. This is going to give us the log, so mu naught ib over 2 pi, natural log from c to c plus a. And that is going to give us mu naught ib over 2 pi log of c plus a minus log of c, which is the same thing as log of c plus a over c. So that is our final answer for the magnetic flux through this rectangular loop. If the field is not constant through the loop or the area is not flat, we have to use the integral form of the equation to calculate the flux.